listening to Data Skeptic, Graphs and Networks, the podcast exploring how the graph data structure has an impact in science, industry, and elsewhere. Welcome to another installment of Data Skeptic, Graphs and Networks. Today we're getting into complexity theory and networks.
When you say complexity theory, people who deal with networks usually think about, complex systems, chaotic systems, and so on. Well, I imagine as a computer scientist, you're thinking about, NP-complete and so on. But
Sure, you should prefix yours. Our complexity will be the default complexity.
We'll talk about it later, yeah.
No, you're right. Good point. Computational complexity, indeed.
Okay.
So vulnerable networks are an interesting topic. I think we've touched on a little bit. We covered Brass paradox at one point, which is a related idea. But how prevalent of a topic is this when studying network science? Is there a lot of concern that there are vulnerable networks?
I guess that's motivation for lots of network scientists. Actually, there's even, I think, a callback to the episode we did with Professor Barzel about networks, right? Paul mentioned that if you remove a hub, usually when people think about removing a hub from a network, it will disintegrate the system, right? Disintegrate the network. But as he said, it's sometimes paradoxically can remove a bottleneck, right? Can make the network go even faster. And that's a callback to Professor Barzel, who mentioned there's a difference, right, between topology and network dynamics. And he showed that sometimes hubs play part of a conductor, but sometimes they are buffers in the network. So you have to know what's the role of the hub in the network before you tackle it, yeah.
If I were in charge of some big network, and I'm going to put my white hat hacker on, I guess in this case, I would want to know if I had an enemy trying to attack my network, but what means would they do it? Where is it weakest? And then try and come up with some plan around that. But unfortunately, I guess what we learn is in the general case, that is an NP-hard problem. So unlikely you're going to brute force the solution effectively on any reasonable size. However, as we get into in the interview, sometimes you don't have to worry about the absolute worst case scenario. For example, most like power grids and transportation grids are a planar network. Under that subset assumption, things aren't necessarily as bad. You can do things in polynomial time that are useful.
We'll usually encounter planar graphs or two-dimensional graphs where edges don't cross each other in a geographical context, where the nodes and edges are geographically embedded. It could be a road network, but it can also be in a very small area, like circuits on a computer chip, right, where you don't want the edges to cross. Usually I don't work with planar graphs, but they introduce some limitations to networks, okay, causing the network to behave differently from other networks. For example, if we look at a road network, because roads are embedded in the ground, the small wall phenomena, which we talked about, doesn't apply here. Even if you believe you have some secret shortcut to when there's traffic, formally it's not considered a small wall, right?
Not a secret passageway, yeah.
Another interesting limitation of the power law. When a network is limited in space, let's say like a neural network in the brain, it has some limitations on it. And when we look at networks with limitations, with physical limitations, we usually don't get a power law. We get a log normal distribution. It means that the distribution, when you look at it at a log scale, it looks like a normal distribution. It's not a normal distribution, right? It's skewed to the left, but still, most networks are not power law. They are heavy-tailed, but not power law. That's why I like to call it a long-tail or heavy-tailed network, not a power law network. It's more correct to say long-tail. My strong belief is that networks aspire to a power law. But because of these limitations like space and time, they usually don't ever reach the perfect power law.
Making it difficult to build an appropriate model that a statistician would be happy with and is easy to compute.
I know people are working on it in the last couple of years. Actually, Barabashi was talking about it a lot last couple of years.
I should have counted all the times we mentioned Barabashi in the season.
Barabashi, can you hear me? This one's for you, buddy. This one's for you.
And I've been calling it network vulnerability. I guess he would call it network diversion, or at least that's the focus of what we'll get into here.
He's trying to divert the flow of the network. doesn't necessarily mean he wants to do it because of the vulnerability part. It could be, I don't know, because people want to control the flow for some reason or another.
An area is going to get flooded soon, and we need those roads shut down. You know,
Yeah, maybe. So I don't think the vulnerability part is the case he's making.
good point. Yeah, yeah. It's how essentially if you're going to take out an edge on that network, or at least that's one of the use cases, or take out several edges, can you do that then divert traffic through a node you've picked? So people on whatever path S to T, are they going to go through your edge because you took out their alternatives? And there's a cost to that. So can you effectively do it?
I think that's also a callback here to the Karate Club, Zachary's Karate Club network, the famous data set, because what Zachary did there was he was trying to, when he tried to cut the graph to two parts, he used the Min.Cut Max.Flow, the idea of parting graphs into two parts. But what actually Paul is trying to do is something a little bit more complex, right? Not just cut the graph in two parts, trying to save an edge between these two parts, right? So,
And interestingly, that makes the computational complexity analysis of it surprisingly difficult. You would think that it's not that much different from sparsest cut or minimum cut, but takes on a life of its own, saying, I just want to guarantee there's one such path.
yeah.
Well, let's jump right into the interview then.
Yeah, my name is Pål Grønås Drange. I'm associate professor at the University of Bergen in the Department of Informatics. So we have an algorithm research group here. Okay, maybe not very large and not very small, but we do some interesting algorithm stuff here in Bergen.
Could you speak to broadly what the group covers?
Yeah, so for the past 20 years or so, we have been mainly doing something called parameterized complexity. That is a quite interesting field, if I have to say it so myself, that studies NP-complete problems. I know you covered the complexity, computational complexity a couple of episodes ago. It covers NP-complete problems. So you can say if you have a problem that is NP-complete and you really want to solve it, right, you have to do exponential amount of work. Okay, so if you want to brute force it, you have to do exponential in the size of the input. So if the input is like a network and you have 1,000,000 nodes, then that function is going to be, or the algorithm is going to run for an exponential amount of time in the size of the graph. But suppose that you have a graph that is maybe it's a tree. Okay, so it's 1,000,000 vertices, but it's a tree. Maybe then you can do run algorithms faster than if it was not a tree. So parameterized complexity tries to look at the structure of the data that you put in. Yeah, try to move the exponent from being the entire input to be some small part of the input.
Is there a universal way of doing it, or is it kind of case by case? You exploit the unique structure of each problem?
The field itself is not very old, but it really took off in the beginning of the 2000s, maybe closer to 2010. It really exploded, and since then there's been a lot of tools, general tools that have come out, of course. So there are some general theorems that you can use to get like wide results, but in general there's, to a large extent, you have to sit down and find out what you can actually use in your situation.
Are there opportunities for industrial partnership? Could perhaps cities or who knows, some big company make use of some of the techniques?
Okay, the most famous tool is something that's called the treewidth, I would say, of a graph. So the treewidth, this is a measure of how close your graph is to a tree. And it's a bit, a social network would be, typically very far from a tree. You have large cliques or large, like dense components, which don't look like trees at all. And also, if you look at a big road network, if you look at, let's say the road network of the United States, it doesn't look like a tree at all. It looks like a grid. Yeah, so that's also not a tree. But maybe sometimes you do actually have things that look like tree. Maybe you have a computer network that is quite tree-like. Then there are very many problems that are NP-complete that you actually can solve in polynomial time, or we call it, parameterized tractable time in this treewidth thing. If you have an NP-complete problem and you want to solve it, sometimes you do, and stuff you want to run your algorithm on looks like a tree, even though it's maybe not completely a tree, then maybe you can use these tools.
Or maybe I could prune my graph just enough that it's tree-like and then take advantage of it or something.
Yeah, that's actually a technique that we use a lot.
Well, I definitely want to circle back around to that, but can we start with just the definition? What is network diversion?
The network diversion problem is, simply speaking, you want to, suppose that you have nodes in your graph. Okay, you have one node called A and another node called B. And let's suppose that this is a road network. So you know that someone wants to go from A to B. Okay, there's this classical problem in graph theory and computer science, which is called the minimum cut problem, which is, suppose that I want to stop people from being able to go from A to B. Yeah, and I want to stop them by removing edges in my graph. Or maybe, if it's a road network, maybe I want to put up roadblocks. Yeah. So suppose you have a city in Las Vegas and a city in, or New York, maybe, right? Las Vegas and New York, and you want to prevent people from traveling with their car from New York to Las Vegas. What is the fewest number of roadblocks you need to set up in order to achieve that goal? So that problem is called minimum cut, and it's a well-studied problem since the 30s and the 50s in graph theory. So network diversion asks a slightly different problem. Suppose that you have a specific road segment that you want to force these people that travel from New York to Las Vegas to go through. Yeah, maybe, if there's like someone if you're law enforcement and you want to capture some people that want to travel from New York to Las Vegas using a car.
Or I own a gas station on that segment of road.
Yeah, exactly. So then the question is, okay, you don't want to cut all roads from New York to Las Vegas. You want to cut everything except one specific road. So that is the network diversion problem. You want to divert traffic from A to B through a specific road segment that you have. The interesting thing about network diversion is that we don't really know if it's NP-complete or if it's polynomial time solvable. So this is, of course, the first part we work on is, can you actually solve the problem in polynomial time? And if you can do so, then yes, good for you. You have a fast and efficient algorithm that you can run on this problem. And if we can't find the polynomial time algorithm, then we want to prove that, it's NP-complete, that probably there will never exist a polynomial time algorithm for it. And once we have found this, then we starting with this parameterized tractable thing. But for this problem that we will discuss, in general, we don't know if there exists a polynomial time algorithm or not. So that's an open problem that I've been thinking for at least 10 or 15 years.
Then it seems to differ from minimum cut in a very subtle way. It's just cut all but one. Am I looking at it correctly? Everyone's talking about AI these days, right? It's changing how we work, how we learn, and how we interact with the world at a tremendous pace. It's a gold rush at the frontier. But if we're not careful, we might end up in a heap of trouble. That's why I recommend you check out Red Hat's podcast, Compiler. This season on Compiler, they're diving deep into how AI is reshaping the world we live in. From the ethics of automation to the code behind machine learning. It's breaking down the requirements, capabilities, and implications of using AI. Check out the new season of Compiler, an original podcast from Red Hat. Subscribe now wherever you get podcasts. In today's data-driven world, the ability to extract value from data isn't just an advantage, it's essential. Mastering analytics can transform both your career and the organization you work for. It's your turn to transform your career and drive organizational success through analytics. Let me tell you about the Scheller College of Business's Business Analytics Graduate Certificate at Georgia Tech. It's 100% online. Scheller College ranks in the top 10 U.S. business schools for busy business analytics professionals. They have a world-class faculty that can help you graduate in as little as a year. But maybe you're busy like me and you want to take it a little slower. You can combine flexibility with rigorous education. Scheller's graduate certificate program adapts to your life, not the other way around. Their program is designed for professionals like us who want to leverage data and solve real-world business challenges, but need flexibility with their time and schedule. That's why you can schedule your classes in a way that makes sense to you. On top of that, you're not just earning a certificate, you're potentially opening doors to Georgia Tech's prestigious MBA programs. Now is the time to become a data-savvy leader with Georgia Tech's Business Analytics Graduate Certificate. Applications are open for spring 2026. Visit techgradcertificates.com to learn more and apply before the August 1st deadline at techgradcertificates.com. Then it seems to differ from minimum cut in a very subtle way. It's just cut all but one. Am I looking at it correctly?
Yeah, exactly. So that's kind of the intuition here. You want to cut everything but one, but it's not so easy because So if you think about it naively, then if you do this, let me just cut everything and then not cut this one edge, then maybe you make a cut, around New York, okay, which means that they can never leave New York. But your road segment that you want them to go through is, somewhere, in California. I don't know. So the problem is really that you want to ensure that they are able to go from New York to Las Vegas and not cut off access from New York to Las Vegas. So yeah, there are very subtle details that make it difficult. So interestingly, with minimum cut, this is solvable in polynomial time. It's famously solvable in polynomial time, and there's been a lot of research on this, and we know quite a lot about this problem. But this diversion problem is simply very different. So there are some cases where we know that it's NP complete on certain, if the graphs are directed. Yeah. So, if your road network has, one-way streets, then you now have a directed graph. Then the problem is NP complete. Whereas there are some cases we know where it's polynomial time solvable. So it's quite different from the minimum cut problem in terms of computational complexity, just due to this one edge you want them to go through. That's why I find it so fascinating.
Well, the roadway network is a great analogy. Does it show up anywhere else? Doesn't seem like it would apply in social networks, but I bet in circuit design and lots of other things, telecommunications, maybe this could be an important feature.
So the class of problems that I'm studying is called graph vulnerability or network vulnerability problems. So a vulnerability measure on a graph just says how susceptible is this graph to some attack. And if you want to talk about, how do you attack a graph or attack a network, then first you have to think, okay, what can I do with a network? And in the case that I mentioned, you can delete edges or remove edges or links from the network, or put up roadblocks, which is the same, I guess. But you can also think about removing nodes in the graph, delete a node or disable a node. So that's kind of how you can modify a network. The other question is, but why would you want to attack a network? Yeah. So then we really come to the vulnerability part of this. Then I guess you have to say that networks exist for a reason, right? All networks have some purpose. You have road networks, they allow you to travel from A to B. Power networks, they allow, electricity company to sell power to users, I guess, and for users to get electricity in their houses. You have computer networks that allow people to transmit information from one computer to another, and so on. And maybe, famously, you have gas networks, like gas pipelines that send natural gas, and you have, of course, water pipelines that send water. But maybe you remember a couple of years ago, you had this case in the Baltics. Suddenly, a couple of explosions took out some gas pipelines, undersea gas lines, right? And you could ask, why would anyone want to do that? And there is these gas lines were transporting gas from from Russia to Europe. If you look at how these gas lines are positioned, okay, I'm not a geopolitics expert, but if you look at how this network looks, then these pipelines called the Nord Stream pipelines, these were the only gas lines that did not go through, Belarus, Ukraine, or Turkey. So that means that if you want to send gas from Russia to Europe and the Nord Stream pipeline is not anymore functioning. Now you have to go through either Ukraine, Belarus, or Turkey. So that's a different thing. That's not a road network, but you have some areas you want to force this transportation to go through, and then what to do? Well, you can take out the gas line, I guess. Yeah.
Obviously, Nord Stream was an attack without getting into who did what and when. Can we say that it was the optimal attack, or can we characterize it in some way using these methods?
If you want to force gas from Russia to Europe to go through either Ukraine, Belarus, or Turkey, then the Nord Stream was the optimal attack. Yeah. So, but that was the only, those are the only lines that you could take out that didn't go through these countries. So it's a bit, it was like a trivial solution of size, 2. But yeah, that was an optimal solution. So if they have like a graph theorist, then this person did their work at least, regardless of who they work for. Yeah.
Yeah. Well, you'd mentioned deleting edges and deleting nodes as an attack. Might someone add a spurious edge or spurious node as a form of attack?
Yeah, of course. So if you have, then we come to social networks. Maybe that's the most reasonable explanation. If you have a social network, you want to. Well, what is the purpose of a social network? That I guess we can discuss that. But you want to keep contact with people, and some people want to sell stuff to people, and some people want to just get information. So if you introduce a node, meaning just introduce an actor, an agent, or a person in a social network, then this person can now start spreading information, right? Either it can be misinformation, or it can be saying things that making it easier to sell stuff and so on. So yes, that is the type of vulnerability that you could look at in social networks. And then the modification thing is introducing fake agents into the network.
Well, unlike a gas pipeline where we don't want to lose even one edge, in a social network, I can lose a friend here or there. Not that that's my goal, but it can happen, and my whole social network doesn't collapse. Does that mean I have a well-structured or less susceptible network?
Yeah. So that is kind of what we study when we study vulnerability. It's like each operation comes with a cost. Yeah. So if you want to blow up a gas line, that probably costs quite a lot. If you want to put up a roadblock, that also costs a lot. It costs both time and money. And if it's a municipality that want to close, or divert some traffic, it costs something in like how the public, like how happy the public is with the current leadership. So you have different types of costs, and what we are studying is basically how cheap is it to attack the network, right? So how much do you have to pay, either by time or resources or explosives, to achieve your goal? And of course, creating like a fake social network user, that's probably not so difficult. But if you have to also have links to people who matters, then that might cost money. So maybe you have to pay to become friends with some influential person or something like this. Yes. Yeah. So the point is, if it costs a lot to attack the network, then we say that the graph is robust, or the network is robust.
How do you model that cost?
Yeah. So usually we have one or more costs or weights per edge or node. So if we go back to this minimum cut problem, one of the early studies were from Ford and Fulkerson back in 1956, I think. This was a military research project where they wanted to analyze the Soviet railway in the 50s to see how easily the Russians or the Soviets could transport stuff from one city to another. And then they actually made a graph out of the rail network, and two computer scientists or mathematicians, Ford and Fulkerson, studied this minimum cut problem on them. And then you have two things, right? An edge, which is a railway, has an ability to transport goods. Yeah, so you can transport stuff. So that's the capacity of the edge, let's say. And then you can say, okay, how much does it cost to attack this railroad segment? Right? How much does it cost for us to actually destroy it? And that's a different cost. That's something that we call an interdiction cost, which is how much do you actually have to pay to take out this edge? So very often in these problems, you have two different kinds of costs. One is, essentially this is how much value does this edge have for the user, and then what is the cost of actually taking it out.
So can we score any graph we want? Look at it and say this one is susceptibility of 7.5 or something along these lines?
Yeah, so this is an interesting question. It again, it depends on the purpose that you have, right? So the road networks, you want to get people from A to B, and power network wants to get electricity somewhere. We have many different definitions of graph vulnerability problems, and many of them are, how many edges or how much do you have to pay to disrupt the network, meaning like how many edges do you have to delete to turn the graph into very many connected components that are all small, right? So again, social networks is not really applicable, but for road networks, you can certainly think of, suppose that I want to like totally ruin people's ability to go from A to B. Like, what do I have to do? And this is so one problem called vertex integrity is maybe one of the most known problems in this vulnerability field.
Well, what does it take algorithmically to assess a graph? I know in the general case we're saying it's NP complete. Can we look at a subset and get some better results?
So in the case of road networks, and I guess also power networks and computer networks and gas networks and like infrastructure networks in general, they have some physical counterpart. So they have what we call a geometric embedding, which means that they exist in some geometry out there. So then you don't have this small world property that social networks have, right? Social networks have this property that maybe the diameter of the graph is at most 6, meaning that between any two nodes you can go from this node to the other in less than or at most 6 steps. This is not the case for graphs that are typically not the case for graphs that have some kind of geometric embedding, like that exist in the real world, right? There's not, you can't go from Las Vegas to New York in 6 using only 6 road segments, right? So once you have this, you get these graphs that we often call planar. So they're not actually planar, but they're close to planar. And then you get much more like interesting theoretical properties. The most famous theoretical result is called the planar separation theorem, which says that you can always split the graph into like big parts using at most the square root of n many nodes, or delete this many nodes. Yeah. But for for social networks and for random graphs, where you have no structure at all, then I don't think we have any good answers to that question.
Well, in the case where we're going to look just at planar networks and I guess as well specifically undirected, what kind of results can you achieve in that regime?
Yeah, so for this network diversion problem, this is this one paper that you mentioned earlier today, that we have a polynomial time algorithm actually for this problem. And well, not to go too deep into the theory, but there's a very nice property with planar graphs and these cut problems. If you suppose that you have a road network, right? So imagine all of the United States and all the roads that you have, but no tunnels and bridges because that ruins everything. But suppose you only have normal roads, then we have a property of planar graphs which is called the cut cycle duality. And the thing is, like, every cut in a planar graph corresponds to something that is called a cycle in the dual graph. So in the dual graph of a planar graph, this is where all the regions of the planar graphs, right? So if you imagine a region is where you have roads around. So a region is someplace that is surrounded by roads. This is called a region. And then you have the dual graph of a planar graph is just the graph that consists of regions are the nodes, and there's an edge between two regions if they are separated by a road segment. Yeah, I suppose that you have two cities and there's a big highway going between them, or like that are separating them. Yeah, then these two big cities are two different regions and they are connected in the with an edge in the dual graph. So in planar graphs, what I'm trying to say is that instead of looking at cuts, we instead look at shortest paths or cycles. And as you know, finding a short path is just, you can use BFS or you can use Dijkstra or something like this. But these are well-studied problems with good algorithms. So for planar graphs, we have some extra tools that helps us when we study cuts.
So not just polynomial time, but in n log n time, which
Yes.
should scale rather nicely.
Yeah. So we actually implemented this, or a master student of mine implemented this algorithm in Rust, and we ran the algorithm on a large variety of networks. And it does actually, we did plot the running time of this algorithm, and it looks exactly like an n log n algorithm would look. We ran the algorithm on some graphs of millions of nodes and edges, and it terminates within, for the largest one, it terminates in half a minute or something, I think. So yeah, this is in my field, this is not really usual that we get these good algorithms, but yeah, we were very happy with this result.
Roughly speaking, how many nodes in that large graph that took 30 seconds to compute?
So for these very large graphs, we created just random grid-like graphs. And I think we had, 2000 by 2000? So that should be 4 million nodes. Yeah, around 8 million edges. Yeah. So we tried it on, it was a random grid, so that, you can, of course, say that sounds very structured. Maybe there are even faster algorithms, but we use completely random weights on the edges, so you don't really have any idea how the cut is actually going to look like when you actually run this algorithm. Yeah.
Well, there's lots of good reasons motivated from complexity theory to be studying these problems, but they also have practical implications. In your opinion, are there any organizations or groups that should be more invested in looking at these techniques? Specifically network vulnerability and things like that.
Yeah, I think definitely that when you look at these gas lines and in this geopolitically tense situation that we're in now, we should start looking at our infrastructure. And I think we should look at the infrastructure in a graph theoretic and network science way as well. Not only, I don't know, not only from an engineering and I don't know, from politics side, but actually from using tools from network science, using tools from graph theory to study. Of course, I don't know, maybe the military does this. So the military were a large part of starting this area, of course. But I think that's there are very interesting tools and techniques nowadays that didn't exist 20 years ago that you could use to look at these problems. Yeah, and also, of course, I talk about attack, how you can attack a graph, but that's, of course, if you're in a defensive position, right? This is what you want to know. How could other people attack our network, and how can we secure it? And of course, that also leads to different problems that we also study, namely that, okay, suppose that you find that your network is vulnerable, then what do you do? And then we have some other problems that we often call augmentation problems. Like, you want to, how can I augment a graph? Meaning, how can I add edges to make it harder to disrupt it?
Well, the techniques that are covered in the paper work on planar graphs, and that's why you get that really nice polynomial time result. Do you think the same tricks or approaches could be scaled up to maybe not do an NP complete problem in polynomial time, but can you take advantage of the same techniques on other classes?
So I'm interested in the in the general problem that's not only on planar graphs, because planar graphs are they're very limited. You could try to generalize it, and the planar graphs are, so planar graphs are the graphs that you can draw on a piece of paper without any edges crossing each other, right? So that's the definition of a planar graph. Or you can draw it on a balloon, and then that's called the genus 0 graphs. So then you also have something called genus 1 graphs, and those are the donuts, right? So everyone who has seen this topology jokes about a donut is a coffee cup, and I don't know. So these are the genus 1 graphs. Can you draw it on a torus without any edges crossing? So you could think, or you could hope, that our technique works for these genus 1 graphs, but everything just breaks down because of this problem that you don't have the thing that I call the cut. I don't know, what did I call it? The cut dual cycle space correspondence. So this just goes out the window once you have a donut and not a balloon.
You'd mentioned, I think, earlier that it wasn't clear what complexity class the problem is in. Is that right? That you're not sure if it's NP complete?
So almost all these natural problems that we work on, like especially on graphs, almost all of them are either polynomial time solvable or NP complete. Very few of them are something else, of the natural problems that appear in the real world. Okay, there are some that are harder than NP complete, but that's not so often. And there are some problems that are in between polynomial time and NP complete, as far as we know. For example, graph isomorphism, right? If I give you two networks, and I ask, are these essentially the same network? Is this the same network? Is this a different drawing of the same network? Then this is called the graph isomorphism problem. And we don't believe that it's polynomial time solvable, and we don't believe that it's NP complete. It's something in between. So there is a class that we call NP intermediate problems. This network diversion problem is definitely inside NP. So it's either NP complete or it's NP intermediate or it's polynomial time. And usually I would say that, most likely it's not NP intermediate, but, after 15 years, I have given up on anything. So, it can be anywhere. Yeah.
Well, if it's not in NP complete, or if we haven't established that, it means no one has shown a polynomial time reduction to and from an existing NP complete problem. What makes that reduction challenging? What's unique about this problem that you can't easily articulate it as another problem?
The way you make these reductions is you find some structure that you can use to build. As essentially, very often what you want to do is you want to take a known NP complete problem and you want to kind of model this problem inside your problem. As it's a bit abstract, but you want to take maybe satisfiability or clique problem or some other known NP complete problem, and you want to model this inside your problem, meaning that your problem essentially solves this difficult problem. So the problem is that it's very difficult to make structures with our problem. So undirected graphs, as you can probably imagine, if you make some graph, then traffic can flow anywhere in this graph, right? So it's difficult to control. Whereas on directed graphs, it's easier to force traffic to go from A to B through this part of the graph and so on. But all of this disappears with the undirected case. Yeah. So it's just it's too little structure to work with for at least for me.
When you think about roadways and trains and that sort of infrastructure, it seems to me the engineers set out to build a safe, reliable system. And in the same way software engineers set out to make the software work, they don't always think to make the software secure. And I certainly I've never worked in roadway design or anything. Maybe they already do this, but it wouldn't surprise me if it's not part of their planning to make the network as resilient as possible. That wasn't a motivator necessarily. With that in mind, do you find that a lot of roadways and things are vulnerable, or have the ways in which people constructed them made them to what degree are they vulnerable in general, I guess is the question.
Yeah, well, I live on an island with a bridge, and
Well, there you go.
taking out that bridge would severely, we would have work from home again,
Yeah.
I guess. But it's also quite a bit expensive, right, to take out a big bridge. And I guess you need a big motivation to actually do it, right? So again, I think in practice, usually people don't want to disrupt stuff, right? Because usually you are a user of the road network yourself, so why would you want to disrupt it? So it is usually just it's in really specific cases where you have disruptors or attackers that want to attack the network. And maybe in the past couple of years, the past 4 years or so, this has been more relevant, especially here in Northern Europe. But yeah, I don't think anything when it comes to gas networks or infrastructure networks in general are designed in such a way that they should prevent attacks from occurring.
Do you think that's a lesson that should be learned, and that those tasks should have these first principles really to avoid vulnerability?
Probably the people responsible for the Nord Stream gas lines are probably thinking now a bit about how can we make gas lines that are spread out, that are more difficult to disrupt, and maybe goes through more friendly territorium that we can control.
Sure, and more redundancy and things like that.
Yeah.
Well, I know graph vulnerability has been around for a little while. Could you maybe characterize, and we've gone through some of the history, but what are some of the major points along the way, and how active of a community is it today?
I would say that it started with Min.Cut as a from an algorithm perspective in the 50s with this Soviet railway studying. Yeah, so it goes actually back a bit before, like to the 30s with Menger's theorem, and this thing that the maximum flow in a graph is the same as the minimum cut. So this is called the Min.Cut Max.Flow theorem, and what it says is that if you want to cut A from B in a network, what you need to find is how many disjoint paths are there from A to B. So essentially, how many parallel routes are there from A to B? Yeah, and this is exactly the same. The minimum cut, this is the number of parallel paths that go from A to B, because you have to cut every parallel path. So that was like, I would say that was the beginning, and then it was studied a bit in the 70s, and it's not clear to me exactly what was the motivation. I think this was purely theoretical. This was just how easy is it to split up a graph. So I think this probably came around when people actually started using graphs in real world, like for real world applications, really programming graphs into a computer in the mid 70s, and then trying to see, okay, how much can we disrupt a graph? So that was in the 70s. And then I think in the 80s and 90s, there's a lot of research coming out of some military operation research journals that you can find on the internet if you just search for it, on how can we disrupt different networks. And one specifically hot topic was the US anti-drug efforts in South America. There they really studied how can we interdict so routes of chemicals coming into certain drug producing areas. So they actually studied quite a lot these vulnerability problems of drug trafficking routes, right? So there you actually have a different kind of defense, right? You want to defend a network by stopping bad actors from using a network. Yeah, so that was in the 80s until maybe early 2000s, and then for a moment it died a bit out, I think. And then in the rise of parameterized complexity again, people started looking at it from this perspective, because now we have tools that can work with NP-complete problems. So I would say before, maybe in the 70s and 80s, once you had an NP-complete problem, you kind of said, okay, we can't solve it optimally, so let's use heuristics or approximation algorithms, and then gave up on studying the optimal solutions. But once we have tools now in parameterized complexity, for example, for actually solving NP-complete problems, then it got renewed interest. So that kind of leads us to where we are today.
And do you have any thoughts on where the field's going?
In parameterized complexity now, we use these vulnerability measures to design algorithms. So essentially what we do is we want to solve some completely different problem, right? Something that is not related to vulnerability at all. But then we can actually find how the network is vulnerable, right? Like maybe it has a small cut, or maybe it has no large connected parts. And then we actually use this to our advantage in algorithm design. This has now become, for the past, I think, maybe 5, 6, 7, 8 years, it has become a tool in parameterized complexity where we use the vulnerability structures of graphs to design faster and new algorithms.
Can you expand on that? Like, what's finding a vulnerability? How do I exploit that insight?
Yeah, so this is the thing is, if there are no large regions of your graph that have very big connections to the rest of the network, yeah. So this is also related to what I mentioned with treewidth, that if your graph is tree-like, then you can separate every part of the graph from everything else with using, few edges. This is kind of the property of having a tree-like graph. And then we design algorithms using a technique called dynamic programming, where you solve small parts of the graph. And then since it has a small connection to the rest of the graph, you can kind of, use this information that it has a small connection to the rest of the graph to compute the results for the rest of the graph and combine solutions easily.
And what's next for you?
Well, I'm going to look at this problem. I've been looking at this problem for 15 years. So that's my next 15 years are also, fully booked on this problem. No, but we also do other, I do some, currently we work on some automatic differentiation algorithms. So where the network appears from like an automatic differentiation setting. You can imagine if you're doing backpropagation in a neural network, right? You're training a neural network. That's of course just a graph. And when you do backpropagation, you want to use some derivatives to update these values. So what we are looking at is just if you have a computation graph, can you make this graph more efficient by removing nodes in this computation graph? And very often when you remove a node, you get more links, but maybe that's something that still makes it faster. So this is one thing that we're currently working on.
Well, Pål, thank you so much for taking the time to come on and discuss your work.
Very happy to do it. Thank you.